Welcome back, everybody. Today we're stepping into a new chapter, but we're asking a question that we've asked before. We're asking once again how we can add up information. And we've thought about adding up information over one-dimensional things before, but now we're actually going to put these one-dimensional things in a new context. Specifically, instead of just integrating a function, say, over an interval on the x-axis, this one-dimensional thing that we have information on is a curve that lives either in the plane or in 3 space. And so in either situation, we get a picture that looks like this. And so here our curve is existing in the xy plane. Here our curve is just kind of floating in 3 space. But the idea in either case is that at each point along our curve, we have some information. Right? At each point xy, we have a function value, f of xy. And over here at each point xyz, we have some function value, f of xyz. And to get a sort of picture of this information, we can, at this point, attach a stick, right, with that function information as its height. You know, if our info was 5 here at this point, well, then our stick could have height 5. And if we do that over each point of our curve, you know, what we're going to end up constructing is a ribbon. You know, that's attached to our curve like this. And a very similar story plays out over here. If at each point we just in 3 space stand up a stick with our function value as its height, and if we do that for every single point on our curve, we'll again define a ribbon that's attached to our curve in 3 space. And what we like to do geometrically, you know, adding up this information means getting a hold of the area of this ribbon. And how this actually plays out is we want to take the ribbon in either one of these situations, we want to lay it out flat, right? So that our curve C actually looks like an interval, right? And here's our ribbon over top of our function information. And what's going to go through and add this up is right here. We use a single integral because what we're integrating over is one-dimensional. And this thing we call a line integral. Perhaps a better name would be a curve integral, since we're actually integrating along just a curve, not necessarily a straight line. But the line is meant to remind us of the one-dimensional nature of this thing. And in any case, this line integral goes through, adds up the information, and hands us the net area of our ribbon. And so this is the picture to have in mind of what we are looking to compute with a line integral. Well, how do we actually compute it? There's 2 steps. Step 1 is we need to parameterize our curve with some vector function. And so here, this vector function is going to have, let's just imagine that we're in the case, let me see if I can zoom out just a little bit, that we're in the 3-dimensional case where our curve is in 3 space, right? And so each of the points on our curve has 3 coordinates. What we'd like to do with this parameterization is come up with a way to move through every single one of these points, right? And so our x component is going to have a function in there, and same with our y, and same with our z. We're going to have three functions of t where we use t values between some a and some b. And so a first step is to parameterize the curve that we are wanting to add up information for. And once we have that parameterization, we can translate our integral. And so here is how this line integral translates in terms of our parameterization. The idea here is that our function, which was originally in terms of x, y, and z, well, here now it's in terms of our parameterization. And so this is kind of a shorthand notation. This just means we want to sub in x equals x of t. So we have some function in the x component from our parameterization. That's going to replace x in our function. And similarly, we'll replace y with what y is in terms of our parameterization, and z is what z is in terms of our parameterization. Next, this ds at the end becomes this over here on the right. So we have dt, and then here it's the size of the derivative of our parameterization. And what this is doing is essentially capturing arc length, it turns out. This S is meant to represent arc length, and the idea here, in terms of getting our net area of our ribbon, is from a certain point on our curve, we want to move over a little bit of arc length and then stretch by our function value to get a little chunk of our area and move through our whole curve and do that. And that's what this formula does. Notice the a and b come from our limits, starting and stopping for our parameterization. Those become our limits of integration. And so here's our translation formula for a line integral once we have our parameterization. And what I'd like to do is look at a particular example to see how this plays out. All right. So here's our example. We want to compute the line integral of the function x, y to the fourth ds, where c is the right half of this circle of radius 4 centered at the origin. So right over here, here is our curve c. And notice it does live in the xy plane. So in terms of a picture of what we're doing, this function here, x times y to the fourth, this is giving us our kind of sticks that we're standing over top of our half circle in the xy plane. So this is the picture to have in mind for this example, something like this. Moving on down, again, we have from our notes above 2 steps to compute this line integral. First, we need to parameterize our curve. And so that is step 1. We want to parameterize our curve C. That says C. And what I want to communicate is, in order to do this, to get a parameterization, we can think about kind of giving instructions like we've already been doing with giving instructions for double integrals and triple integrals. And so I want to show us how that can play out from really a couple of different perspectives. The first perspective we'll take is that, hey, this curve is, part of a circle. Well, polar deals very well with circles, and so let's think about that, right? If we were doing, say, let me get caught up. We want to think in terms of polar to start, to get our parameterization. If this was a double integral, and we were integrating over the full right-hand side of this circle, if we were thinking about in terms of polar, we'd say, oh, well, we're gonna, for each angle, we'd let r, start at 0 at the origin and then move out to r equals 4. And, the thetas we'd use are from -pi/2 up to pi/2. Right, well, here, we don't want, the guts of this circle, we just want the edge. Right, so we don't want to let r start at 0 and then move out to 4. We just want r equals 4. Right, we just want r to equal 4. And what thetas do we want to use for this? Again, the same thetas, -pi/2 up to +pi/2 will work. So this is our description of our circle in terms of polar coordinates. But notice for our parameterization, we need x and we need y. And so we need to take our polar description and translate it using our formulas that we have on hand already for translating polar to rectangular. Right? X is r cosine theta, y is r sine theta. And here from our description for our curve here, r is always equal to 4. And so we can actually just go ahead and plug that in. All right, so this x becomes 4 cosine theta, and y becomes 4 sine theta. And right there, we know what our x is, we know what our y is. We can take these and now just plop them in to the x and y components to get our parameterization. And so putting that together, our parameterization, which, by the way, we're probably expecting a t to be showing up. We could relabel these thetas as t's. That would be fine, but there's no need to. This t is just a placeholder name for whatever our parameter happens to be. And in our case, our parameter is theta. All right, so I'll just make a note that our t is theta. That's what we're using as our parameter, and that's fine. We can just leave it like that. So our parameterization, right, which gives us our x and y coordinates of our points on C. The x component is 4 cosine theta. The y is 4 sine theta. And the thetas we're using, right, are -pi/2 to pi/2. And so there's our parameterization. And over here, these bounds on theta, these are our a and our b in terms of our general formula for line integrals that we saw earlier. All right. Well, now we have successfully parameterized our curve C. Now all that's left to do is to go ahead and translate our integral using our formula. Let me maybe just head back up, just remind us what that is. All right, so the line integral translates to this integral in terms of our parameter, where our function, all of its variables just get replaced with what they are in terms of our parameterization. And then we have this extra thing to compute the size of the derivative of our parameterization. So what that becomes down here, I'll just scroll all the way down. So here's our function, xy to the fourth. And so here, this 4 cosine theta, right, that just gets plopped in for x wherever we see an x, and the 4 sine theta similarly gets popped in for the y here wherever we see it. And so making those replacements, x becomes 4 cosine theta, y becomes 4 sine theta to the fourth, right, because we had y to the fourth here. We have our limits for theta as our limits of integration. And then what goes here, right, is the size of the derivative of our parameterization. So just a little bit of work here to do that. Here's our parameterization, taking the derivative with respect to theta. We're going to get 4 negative sine theta for the x and 4 cosine theta for the y. So here's the derivative. And we take the size of this vector like we would any other vector. In this case, just Pythagorean theorem, right? We get square root of our first component squared plus our second component squared. And to work from here, right, we can do this trick that we've done before. We have a common factor of 16. We can pull that out inside the square root. Sine squared plus cosine squared equals 1. And here's that 16 that we pulled out. And so what we're left with is root 16, which is 4. And so that is exactly what we pop in here in its place in the formula. And at this point, the dust has settled, and we really have completely translated our line integral in terms of our parameterization. And at this point, all we have left to do is compute this, at this point, just a Calc 1 integral. Right? So notice there's a little bit of simplifying we can do. We have a 4 here and a 4 here. We actually have 4 4s when we distribute this fourth power. And we have 4 sine thetas all multiplied. And so we're going to have 6 factors of 4 altogether. So we can collect those here. And we have a single cosine and then sine to the fourth left over. And so here, this is the integral we need to compute. We need to find an antiderivative. And pop quiz, how could we find an antiderivative for this function here? If you said u sub, you're right. This is definitely a u sub integral. Right here, the idea is the sine fourth is really sine theta to the fourth. And so if we let u be sine theta, that's a nice inside function. Its derivative is actually literally floating around right next door. And so u sub will clean this up considerably. I'll let you work through the details. Here's the final answer for our net area over our curve through our function information, about 1600-ish or so. So lots of area. So right there, that's an example of how we can look to compute a line integral by first parameterizing our curve, by kind of giving instructions, and then finding what our x and y are for our parameterization. Right, if we were in 3 space, we'd also need to find z. And once we parameterized, then we can go ahead and translate our integral using our formula and just crank it out from there. I wanted to show us one other perspective on this example. Up here, thinking about parameterizing our curve, polar is certainly the most natural way to do this, right? It's half of a circle. So polar is certainly the way to do it. But let me take this opportunity to mention that we wouldn't have to use polar if we didn't want to. You know, if we were doing a double integral over the whole filled in circle, well, if we really wanted to, we could set this up with rectangular as well. And so let's talk through that. It'll give us a chance to mention a useful idea. And so here, and if we really wanted to, we could think in terms of rectangular. And the idea here is that this curve, I claim, is the graph of a function, but not a function of x, right? At a particular x, there's two different y's on our curve. So it's not a function of x, but it is a function of y. And because this is a function of y, we can set up a parameterization with y as our parameter. We'll just kind of talk through the idea. So the idea is, going back to kind of the double integral situation, if we were trying to give instructions here, we would say, okay, let's set y and move x, starting from 0 up to the circle. And then if we had a different y, well, we'd start x at 0, move it out to the circle. But here, right, in our line integral, we don't want the guts of this circle. We just want that outer edge. So at a y, we don't want to start x at 0 and then move it out to the circle. We just want the x where we're on that circle. And so what we can do is that we can take our circle equation here and solve it for x. And once we have that, we'll be able to just plop it in for our x component and leave y alone, since we're using y as our parameter. So y can stay. So what that looks like here, if we solve this for x, toss the y squared over, x equals plus or minus root y squared. So we have, that's just showing us that our circle, the full circle, has a positive x side and a negative x side, right? Because of where our circle lives, we want the positive x side. And so right here, that's what we can now just take and plop in for the x components in our parameterization. And so right here is a nice parameterization of our circle in terms of our parameter y. And again, the values for y that we would use, they're still the answer to the question, what y's do we do this for? Well, we'd want to start y at the bottom, -4, and grab points on the circle until we get up to +4. And so right here, this is a legitimate parameterization of our curve that we could use to then go ahead and translate our integral using our translation formula. Let me mention, so using rectangular for our particular integral would not be fun. Polar is definitely the nicest way to go here, but for perhaps other curves, this is a very, very useful idea to keep in mind, that if our curve is a function of a variable, in this case y, then we can use that variable as our parameter and figure out the other components. All right, that's it for today. We'll definitely play around with these ideas some more in the coming lectures. Good work today, everybody. If you have any questions, post those to Piazza, and I'll see you next time.